So the theorem 6 is for Rabinovich, which says that if a tree metric alpha deterministically approximate the n cycle, then alpha is constant number of n, is order of n. And of course, we don't need this in this article, but I just want to say we just need the definition 7, which says that a hierarchically well-separated tree, K hierarchically well-separated tree, is defined as a rooted weighted tree with the following properties. First, the edge weight from the node to each of these children is the same. So each of the children, the node is the same. The weight is the same. All of these are node of the same. And the edge weight along any path from the root to a leaf are decreasing by a factor of at least k. So when it goes to the leaf, the weight is decreased by a factor of k. And so the height of a tree is the maximum number of edges on a path from root to leaf. Let's denote it by h of t. And note that a k hierarchically separated tree, k HST, has a weight h of t less than log of diameter of that t. And the final definition that you need to know before I say the main theorem is that an L partition of G is a collection of vertices. P is V1, Vs, such that Vi is in V, and the union of all Vi's are V from I between 1 and S. And so there is no intersection. Also, there is no intersection between them. It is 0. And because for all I and j is less than S, Vij is not empty. The intersection is not empty. The intersection is empty. They are disjoint. I want to say that there are disjoint sets. And finally, C of Vi is the subgraph of G induced by Vi. From this lecture to the next lecture, and you will see that when I say subgraph induced by Vi, I mean C of Vi is like this. For example, we have a shortest path decomposition. We get the induced graph by just cut the vertices of that shortest path, and you get many constructions in computer science by just doing this. And the strong diameter of Vi is bounded by diameter of C of Vi, and the goal is that in each stage, for example, you have your first of all, the diameter is bounded, and second of all, you will see in the next lecture that we try to bound it to make it smaller and smaller, so that for example, I will explain in the next lecture. But let D be a probability distribution over a set of L partitions, and consider, for example, an edge, U and V. And X of E is the probability under that distribution that U and V belong to different clusters. For example, this is V1. If you induce the graph by V1, when you're removing that, we have two clusters. And so this is V, this is U, this is the edge I said. So what is the probability that one vertex of this edge is in one cluster and the other is in the other cluster? And these are the historical ideas that provided things like padded decomposition and alpha beta padded decomposition, and that's why for historical purposes I have to say. Otherwise we have much more powerful constructions in the next lecture. Definition 11 is said that an R, rho, and lambda probabilistic partition of G is a probability distribution over a set of R row partitions of G such that the maximum of this probability times R divided by the weight of that edge is less than equal to lambda. And the probabilistic partition is epsilon forcing if for every E in E we have the weight of that divided by R is less than equal to epsilon, then we say that this probability is just zero. This is the concept of epsilon forcing. And the main theorem is that the theorem of theorem 13, that it says that if there exists R, rho, and lambda probabilistic partitions of any subgraph of G, then G is alpha probabilistically approximated by a set of K hierarchical separated trees of diameter of T is order of diameter of G. So we have so this theorem says that we have a graph G, we can approximate it, alpha probabilistically approximate it by just a set of K hierarchical separated trees, and then trees are like each other, so approximation of beta, approximation of alpha, so we have approximation alpha beta. This is the idea. And so it remains to say the construction of these probabilistic partitions. And that's why theorem 14 says that, of course, before that, I want to say how to construct it, how to construct those probabilistic partitions. So the construction is very easy. We say that the ball of V, I mean all the vertices of the subgraph H, such that the distance between V and U is less than Z. So Z here is the bound on this and on this. So it is the radius of that, but centered on V. So this is just a ball. And we construct one cluster of the partition at each stage. For example, at the stage T is equal to 1, we create only one partition. At stage T equal to 2, we create another cluster. Until at the last stage, T equal to D, that everything is now partitioned. So you got the idea. So I've decomposed it into 3, 4, 5 clusters. But we do it in a stage. That's why many people, when they read these articles, they don't understand. Because it uses different concepts. And so at this page, this is S and then S bar. At this one is, you are creating clusters, but in a hierarchical way, in stages, not at once. And so we construct one cluster of the partition, and at the T stage here, there is associated subgraph H of T of G that is induced by a vertex set UT, which is a subset of V. And at the beginning here, it is the subset is V, and the induced graph is the whole graph. And then when you go down, things are opposite, because finally the subgraph is the subgraph that we use, the data that we use for inducing, to make an induced graph, is now less and less, but the clusters are growing. For example, here it's just one cluster, here two cluster, but the clusters are now growing. So we have more and more clusters. And but the algorithm, precisely, you can say that we repeat the process until that ut is equal to 0. It means that we don't have any point or set of points to create an induced graph. And it's a very interesting idea. And let v of t be an arbitrary node in u of t. So this is v of t and this is u of t. So if the connected components of h of t, including v of t, has diameter at most 2r ln n, then define it to be in the next cluster. So we have no problem with that. Otherwise, which happens most of the times, we do like this. We say that we consider the real interval between r and ln of n, and now choose the radius z. So this is the ball, the radius z. So this is the ball of radius z of a point center v of t. So this is v of t of subgraph h of t. So this is the next cluster. I mean, we define the subgraph induced by this ball. And this is the next cluster. We call it c of t. And so h t plus 1 is the subgraph of g induced by vt plus 1. And this is a loop. So, but the analysis, so first, so this is G. It has some vertices. First, at first stage, we have this cluster only, and the rest. And then at the second stage, at the third stage, at the fourth stage. So when I'm increasing these clusters, you see a point has a better chance. I mean, 2 points have a better chance to be close to one of those clusters rather than... So the distance between any point to any cluster, to the nearest cluster, this distance is much less than the distance between x and y. And if you get this idea, then you know why probability is the main role of this construction, and why probability is very interesting. Why at the first stage, this what happens when the stages grows? When the stages are increased, we have more chance to find the close cluster. And the distance between this y and that cluster is much less than distance between any other point. And by chance. And so this is the idea and intuition behind the future articles of Itai, Abraham, and people like Yair Bartal, all of them from Israel. And so these are very interesting constructions in computer science. I mean, the most interesting constructions in computer science is just about these probabilistic random partitioning in the context of metric embedding. And many people are not aware of that, because they are either concentrated on metric labeling, or they want to use it for traditional algorithm. K-way cut, K-cuts, multi-way cuts, and many of those traditional algorithms. But metric embedding has, the works of these two guys are really inspiring, and it is growing machine learning. It will grow machine learning in the next 20 years, definitely. Nowadays, machine learning guys are not aware of these advancements in metric embedding, but in the next 20 years, many people will talk about these algorithms. So let's carry on and see what it terminates at. So the probability is n 1 over r e to the this one, and of course in the final step of the algorithm you have so at each stage you remove those after inducing that and removing those vertices, you get some sets. And so let's talk about the analysis of that. Analysis. So the bound on the radius of the partition is obvious from the description. And so consider the edge, which is U and W. So our goal is just to bound the probability that E is included in none of the clusters. It means that if you have some clusters, one vertex of an edge, U, is in one cluster and the other one is in the other cluster. So this is the edge E that it may or may not happens, because our construction is just probabilistic. And from the stage T, we know that V is VT is let's say this is the vertex chosen. So this is V of T, and so Z is the random radius. This is Z. This is Z is the random radius chosen at the Tth stage, and we define the events in the construction with respect to the edge E, with respect to this edge. And we assume that without loss of generality, we can use D of V of U is less than D of V of W. And so let's say that AT is the event that U and W is in UT. We have M1T, as you are reading the article, it is the other event, the event that D tilde of V of W is less than that radius, this radius Z. So the distance between them is less than radius Z. And conditional on A of T, of course. And this says that the edge U and W, it is inside C of T, is inside that cluster. We have another event, MTN, MTX, which is the event that D of V of U, D tilde is less than 2, is less than D tilde of V of W, and the U is included in that cluster, but the W is not. And therefore, the edge U of W will be excluded from any cluster in the partition. And we have MTN, which both U and W are not included in the cluster, in the C of T, and therefore pass to the next stage. We need more stages. And finally, we have XT event XT, which is the event that none of the clusters, that U and W is in none of the clusters. And note that the probability of A0 is 1, And you can see the proof that